Welcome to our Quantum Deep Dive. Today, we're exploring a fascinating essay by Jörg Owe Schnuppet. It gets right into one of the biggest, and I mean biggest, challenges in data science today. How do we make any sense of all this overwhelmingly complex information? Yeah, the author just nails it with this quote right at the start. We're literally creating more data than we can possibly wrap our heads around.
Exactly. And like he says, this isn't just about making things a little easier. It's about whether we can even find the breakthroughs hidden inside these giant data sets. Without cutting through the noise, we're basically lost in the dark.
So, to really unpack all this, we're going to take you on a little journey through these 6 key stages.
Yep, we're going to start with just how huge this data problem really is, then look at why our current tools are kind of hitting a wall, and then, this is the exciting part, we'll dive into how quantum computing offers a totally new way of looking at information.
Okay, so let's jump right into our first section, the unseen data universe. Because before we can talk about solutions, we really need to get a feel for the unbelievable scale of the data we're dealing with. And we're not talking about a small step up. This is a full-blown explosion of complexity. Right, and this little expression right here, O to the power of n, this is the heart of the whole problem. It's how the data you need to describe a quantum system with n qubits just blows up. And to give you a sense of how huge that is, if you have just 50 qubits, the number of values you need to store on a normal computer is over a quadrillion. Well, it's just not going to happen. It's totally impractical. And this isn't just some abstract theoretical problem. This is happening right now in fields that really matter. You've got particle detectors at places like CERN just spitting out fire hoses of data every single second. Or think about biology, where one person's genetic data can have millions of different features.
For sure, and it's also a huge deal in AI and finance. The hidden layers in those complex models, what they call latent spaces, are unbelievably vast. We're creating data that lives in these enormous, high-dimensional worlds that we just can't explore with the maps we have now.
Okay, so how have we been handling big data up until now? Well, we've got some really clever tools in our classical toolkit. You could call them the old heroes of data science. They've been the workhorses for years, but as we're about to see, they're starting to show their age. A real classic, which is broken down here, is called Principal Component Analysis, or PCA. The easiest way to think about it is to imagine a big cloud of data points that looks kind of like a stretched out football. PCA is amazing at finding the longest axis of that football, the direction where the data is spread out the most. It then squishes all the data down onto that line, keeping the most important trend and getting rid of the less important stuff. Right. So this slide kind of contrasts the two main flavors of tools. On one side, you have that linear approach of PCA, and on the other, you've got these really powerful nonlinear methods like t-SNE and UMAP. They're much better at understanding complicated, tangled-up relationships, and they make these beautiful data visualizations.
But, and this is the big but, here's the catch. Both of them, the simple linear ones and the complex nonlinear ones, are basically hitting a brick wall.
And this is exactly where things start to break down. We run into these fundamental roadblocks. As you get more and more dimensions, this really weird thing starts to happen. Every single point starts to seem equally far away from every other point. It's called the curse of dimensionality, and it just shatters the logic behind a lot of our algorithms. And that's not even counting the sheer computational cost. These calculations can take forever, and the amount of memory you need to even store the data can be more than our biggest supercomputers can handle. We're just running out of road. So, that brings us to the quantum leap. This is where we start to see a completely new path forward.
And it's so important to get this. This isn't just about building faster computers. It's about using computers that work on the exact same principles as the ridiculously complex data we're trying to figure out. We're talking about a fundamentally different reality.
This slide just lays out the core difference perfectly. On the left, you've got your standard classical bit. It's a simple light switch. It's either on or it's off, a 0 or a 1. That's it.
But then you look at the qubit on the right. It can be a 0, a 1, or, and this is the mind-bending part, it can be a mix of both at the same time. That's called superposition. And it means a handful of qubits can hold an exponentially bigger amount of information.
Right. So quantum computers work in these gigantic mathematical playgrounds called Hilbert spaces. You can think of it as the native language of quantum mechanics. The whole reason quantum data is so complex, remember that O to the 2 to the n growth, is because it naturally lives in a Hilbert space. So a quantum computer isn't intimidated by all this complexity. It's right at home. It's built from the ground up to navigate these massive data landscapes because it plays by the exact same rules. Okay, so if quantum computers are speaking the right language, what are the new tools they actually give us?
Well, the essay points to three really big approaches. And what's cool is that they kind of mirror our classical tools, but they operate on a whole new level of power.
So first up is QPCA, or quantum PCA. And yeah, you guessed it, it's the quantum cousin of the classical PCA we were just talking about.
But here's the key difference. Instead of building a giant spreadsheet of data points and doing math on it, QPCA works directly on the quantum state itself. It analyzes something called a density operator, which is the quantum way of describing the data.
And this is where the real quantum magic kicks in. Instead of trying to wrestle with that enormous matrix, QPCA uses this incredible technique to basically just ask the quantum state, hey, what are your most important features?
It pulls that information out directly, without ever having to write down that impossibly big matrix. And the payoff is huge, a potential exponential speedup. It just scales so much better as the data gets bigger.
All right, next up we have QSVT. You can think of this one as a kind of universal Swiss Army knife for doing math on a quantum computer.
Totally. So inside any data set, you have these things called singular values that basically tell you how important different patterns are. QSVT lets you go in and mess with those values directly. So for example, you could just tell it to zero out all the small, unimportant values, which is a super powerful way to filter out noise and compress your data.
And last but not least, there's the quantum autoencoder. Now, this is a machine learning approach. It's basically a quantum circuit that you can train, kind of like you train a neural network, and its whole job is to figure out the absolute best way to compress the data. It literally learns how to squeeze all the important stuff into a few storage qubits while shoving all the useless junk into some trash qubits that you can just ignore. It's an unbelievably flexible and powerful idea. Okay, so these tools sound amazing in theory, right? But what does this all actually mean for the real world? This isn't just a cool science project.
Not at all. The applications that the essay lays out are genuinely transformational. We're talking about things that could completely redefine what's possible in science and tech.
I mean, just look at this table. In chemistry, this could mean we can design new drugs and materials by simulating molecules in a way we never could before. And for AI, it could unlock a new generation of smarter, more efficient models by feeding them this super compressed, potent data. In finance, you can analyze these insanely complex risk models to maybe even prevent the next big market crash. In every single one of these fields, this is a game-changing technology.
But, and there's always a but, we're not quite there yet. Which brings us to the future of all this.
Right. Like with any truly revolutionary technology, the road ahead is still filled with some pretty big challenges, the kind that researchers all over the world are working on right now.
First up is a big one, the data loading problem. You can have the fastest quantum algorithm in the universe, but it's pretty useless if it takes you 1,000,000 years just to get your data into the quantum computer. Then there's the hardware itself. Today's quantum computers are noisy, which means little errors are constantly creeping in and messing up the calculations. Building good error correction is like the holy grail for making these things actually scale up. And of course, once we get an answer, we have to be able to understand and trust it. So this whole deep dive, which is based on that great work by Jörg Oeschnabet, it really shows that we're standing on the edge of a massive shift in how we see things. We're moving way beyond just collecting data.
We're actually learning how to draw entirely new kinds of maps that will let us explore these huge universes of information that have been completely invisible to us until now. Which brings us to that final question. If data really is the new landscape, what incredible worlds will these quantum maps finally reveal?
To really dig into this topic even more, we definitely recommend you visit schnappot.be. Thanks for listening.
Goodbye.
Goodbye.
Schnappot.de is a private project by Jörg Oeschnabet dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.